start.
factorial.
I hope this will not be hard. What do we do today? First, let's finish the work from last time. We didn't finish the proof of Pascal's formula. And I think it's a good idea to go to this important proof, to emphasize it, and then to practice with the technique from there. Then we'll do one application that's also in the code. I don't know many of you maybe saw it. And then we'll go to binomial formula, which is a fairly easy topic, but very important and very useful. And that actually very naturally connects with what we studied in section. So, here's Pascal's formula. It tells you that choices actually have a very interesting property. And that is that if you take two choices that are next to each other, they're both out of n elements, and next to each other means r and r plus 1. When you add them up, you will get choose on the next level and plus 1, choose r plus 1. But actually, to preview the story for what we'll do today, instead of calling them chooses, because nobody calls them chooses, everybody calls these numbers, they are called binomial coefficients. And we'll see in a moment why. So by now, just let's accept the terminology. So this is property of binomial coefficients. And the proof, I'm not going to do proof by induction because it's complicated to go from one step to the other with these objects before we have this. Now when we get this formula, we'll be able to do proofs by induction, but without it, I wouldn't do that. I would just go by definition. So left side equals, I will open both of them by definition. What would that be? N factorial on top, what on the bottom? Times what? N minus r factorial. Is this just definition? And then the second one does almost the same. N factorial, r plus 1 factorial, n minus r minus 1 factorial. Is this just definition?
Yeah.
You understand why it's minus 1? Because I've subtracted r plus 1. And there's only one ingredient. By the way, you'll see once I assign this as a exam problem, because it is, you know, it shows how if you have no command of the factorial technique, by the way, you have to have it also in your calculus 2 class. Calculus 2. So we are looking, n factorial is the same on both, do you agree? What about these factorials? One is longer than the other. Who's longer, r factorial or r plus 1 factorial? So what we'll do, we'll keep r factorial the way it is in n factorial. But we'll split r plus 1 factorial as r plus 1 and then r factorial. Do you agree with me? Because you start with r plus 1 and all the others are just r factorial. What about these two guys? Who is longer? N minus r factorial or n minus r minus 1 factorial? So I'll copy n minus r minus 1 factorial and I'll break this one with that extra steps. Extra step n minus r, and then all the others are n minus r minus 1 factorial. So after we did this, those two fractions have lots of things in common. Because this is the same, this is the same, and this is the same for both of them. Don't you agree? Can I factor that out? So if I factor it out, I'll get the following. N factorial over r factorial over n minus r minus 1 factorial. What's left on the first one? 1 over n minus r. What's left on the second one? 1 over r plus 1. What do we do now? We need to add two fractions. So what do we do? Common denominator, but they're just a product, so we just cross multiply and add them up. So it will be n factorial over r factorial n minus r minus 1 factorial. When you cross multiply, you get we are done. Why are we done? Because this is a moment. R and R cancel. So now we will assemble factorials. So what is this? N factorial times exactly the next member n plus 1. What is that? N plus 1 factorial. What about on the bottom? The same story. R factorial and this R plus 1, which is just the next member is what? U factorial. Which one? R plus 1. What about the other two? Is that again continuation? N minus R minus 1 factorial, and the next member N minus R, that's what? And then with a little doubt, I would say that this is equal N plus 1, choose R plus 1. I put a little mark. Are you sure about this? Let me check by definition. What do I get on top? Do I get N plus 1 factorial, yes or no? Then bottom 1 factorial, here it is. What is their difference? If I subtract them, what do I get? That's right? So proof didn't use any induction or anything, just definition and simple algebra. Break factorials so that you can combine them to make common denominator. Then when you get them together, assemble factorials again. So what is the nice consequence of this one? If you look at all the chooses, or all the binomial coefficients, then they exactly look like in that Pascal triangle, and this justifies Pascal triangle. So if you have 0 elements, you can choose just those 0 elements in one way. If you have 1 element, then what can you do? Either not choose it or choose it, which is in one way both of those. If you have 2 elements, if I have n equals 1, n equals 0, if I have 2 elements, then what can I do? I can choose none, and that's in one way, or I can choose 1, and how do I get that to choose 1? Can I add 2 consecutive binomial coefficients on the previous level, and that would be 2. So that's 2 choose 1. To get 2 choose 2, at the end we always have 1s. Again, 1 and 2 here will give you what? 3, and that's exactly Pascal formula. 2 members on the previous level with the next one, and then 3, and then 1, 1. What is this? Is this 3 choose 1 or 3 choose 2? 3 choose 1. No, you start with 0. This is 3 choose 0, 3 choose 1, 3 choose 2, 3 choose 3. This is 3 choose 1. So let me look at this triangle here. Who's this? This is 2 choose 0, plus this is 2 choose 1, equals 3 choose 1. And that's exactly what our equality looks like. Let me do one more example. N equals 4, 1, 4, 6, 4, 1. How would you read this? How would you read or justify why is this 6 here equals 3 plus 3? This 6 here is what? 4 choose what? 2 equals, what is this? 3 choose 1 plus 2 consecutives on the previous level, and then are equal to 1 member on the next level with a higher of those 2. So it matches exactly. And it's interesting how geometrically it looks that half the side of a triangle shift makes it all match very nicely, makes like a fractal. And then we can get any line of this triangle. What is this triangle useful for? Is it recursive? Can I fill in line 20 without filling the lines 19, 18, and 17? I cannot. So I have to go line by line to complete it. But what is good about it? In line 20, it gives me all the binomial coefficients. Do you agree? So I get immediately 20 choose 0, 20 choose 1, 20 choose 2, and all of them. So if I need all of the coefficients, this is very nice. And then I like this problem. That's why I chose it as an example, because it is in full contrast with what we just did. I think this example 437 is very nice. of facts about binomial coefficients are often very, very interesting. Sometimes you apply algebra, like we did here. Sometimes you apply modeling. You tell a good story and the proof comes in. So here is the story that justifies this. Imagine that I have two n elements, n stars, and n squares. Okay? So, and suppose that I put them all in one head. So it's how many objects altogether? I mean, in general, if it's n, you don't read picture, you read the label. So is it 2n?
Yeah.
And suppose I'm choosing n objects out of those two. So I don't care who is who. Just I go there 1, 2, 3, 4. When I do n, I stop. Might be stars, might be squares. I don't have a way to recognize. Is that exactly this side, isn't it? So I did the modeling story for that. So what happens? Then I say the following. So all those possible choices, now I'm going to classify differently. What would happen when I choose n of those objects from the head? Could they be all stars, yes or no?
Yes.
So it might be all stars, or what? All stars by what? But one. Stars but one. And that one is obviously a square. Or what? All stars by 2, da 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 da, and the end all squares. Do you agree? You clearly see this or. These are alternatives. I'm not assembling, so I'm not going to multiply. I'm not assembling those with all stars and all that have all squares. Do you agree? So I'm not going to multiply. I will do what? Add. Be careful. Is there an overlap? Can the same choice have 3 stars and 5 stars? No, it cannot, because it either has 3 or 5. So there's no overlap. I can do clean. All right. If I take all stars, in how many ways can I do that? How many stars do I have? N. How many do I need? All n. In how many ways can you choose n out of n? Only one. Choose n. What if it's all stars by but 1? Now, I have how many stars? N. But I choose not n, I choose what? N minus 1. But then when I'm done choosing stars, what do I need to choose? Square. How many squares do I need? 1. Out of? And then do I assemble that? Yes or no? When I have my star choice and my square choice, do I get them together to have a full lineup? What is that telling you? We're going to do with numbers? Then what if I want 2 squares? Then the same story. And then minus 2 and 2. Da, da, da. At the end, it will be just n. And that's exactly what we have up there. Or maybe not exactly. What do I do here? Doesn't look like what I had there. What should I do here? Because I didn't get those squares. But there it is.
For the first one, you can define it.
Let's forget first one. That's the degenerative one. This will give you a better idea. Yes?
Use the complement.
The complement. N choose n minus 1. Is that the same as n1? Yes or no? So this one and this one is the same number. So generally this could be traded for n choose 1. And then here n minus 2 can then be traded for n choose 2. Yes or no? Or n, I needed n, no. I traded everything for n minus 2. And then the last one both will be traded for n. So what about this one? I didn't write. If I choose all n stars, how many squares am I choosing? 0. So that's why I get square again. So it's n0. This is going to be traded. So I get n0. And now I bring it to the trading. Exactly get what we have there. Which got this equality showing two different ways to count this group of objects. Once we just counted generally combination, we didn't care who is in there, and then we carefully classified according to the number of stars and squares. It must be the same count, and that's what proved this identity. So I like the fact that here they stand next to each other, one showing just brutal force of algebra, and the other one showing good modeling that actually saves you from big algebra, and you get it quite quick. I didn't open factorials or anything, just it showed up very nicely when you move it. All right, so that was the story. The end of the story about combinations. Maybe we have like, before we start section 4.4, maybe we have 5 minutes to do one of the problems. Would you like to do one of the problems on the board? Any specific requests? Just don't say any, that means you're in trouble.
What about the next part? What kind of the exact number? B, 5B.
5B, what is this?
How many ways to get 4 with 9?
4 of a kind. Oh, that is? Okay. So there are 52 cards. And those 52 cards are organized in 4 suits. And they are what? They are diamond, and heart, and spade, and club. These are 4 suits. And in each of them we have 13 values. Some of them are numbers, some of them are faces. So those are the numbers what? 2, 10. Then there's ace. Some people think of it as 11, but it doesn't matter. Jack, queen, king, and ace. Very often ace is just thrown this card in the game. So that doesn't the order really is irrelevant here. So that's 13 of them plus 9 and 4, 13. So they're all together in each suit. You have 13 of those values. So altogether that's 50. Okay. Now it says. How many poker hands have 4 of a kind? So to do a poker hand, we are choosing 5 cards. The order doesn't matter. Why? Because order would matter. It doesn't matter how do I keep it in my hand or how do I get it from the deck. No idea. You shuffle them however you want. So obviously these are combinations. Order of cards, how you keep them in the hand, doesn't matter. And then what? So if I'll think of kind of designing that type of card. So there is 4 here to design that are all the same, and then there is 1 extra card. So first, I'll design this value that repeats 4 times. Who could be there? Either 2 or 3 or 4 or 13. 13 ways to choose long value. So what we call long 1, long 2, long 3, long 4. That's 13 ways. Do you agree? Long, because this is long, 4 of them, and this is short, just 1. Because there's also, when you have full house, there's 3 and 2, and I like to call them long, or however you want to call them. All right, so here, when I decide that I want 7s here, do I choose those 7s or all 4 7s are equal? All 7. So I only need to choose which value is on long. Agree? When I'm done, and it could be 13 ways, then I choose who's on short. In how many ways?
48, 1, 1.
He says 48. Do you agree? Yes. The only cards that cannot be used are these 4 that are already used. Do I have any restrictions? No. So anything. Then what do I do with these numbers? Multiply, because I'm assembling these 4 and 1 to give me 5. choose here and say, no, I want first to choose the value and then the suit. Yes, how many values are left? If one is gone, how many values are left? 12, but the moment when you choose that you want, let's say, queens, then what do you also need to choose? Which queen out of those 4 is there? So you need 12 times 4 is the same. Either way, there are different possible ways to think of this. And then if you choose, but more interesting is the next one, the full house. Then it gets a little trickier. Why? Let me do C, since we are already there. So I need to choose a long one and short one, agree? And then of course, if I flip long and short, that will be different full house, different strength. So what the first thing? First thing is, who will be my long value? So who could be my long value? Same way as before. Any of those 13, agree? So in 13 ways I can choose the long value, but I'm not done yet. The moment when I commit, let's say, to kings, then what do I need to decide as well? Which 3 out of 4 are there? So it's 13 times 4. That makes sense? So not only which value, but in that value, which cards are chosen. So what happened? Imagine that I already filled in these 3 spots, right? Now I'm doing the second half. What do I need to do now? To choose my short column. How many ways? 12 ways, because there are 12 remaining colors. And then what do I need to do when I choose the second column? That's the second value, not color. Sorry, choose 2. 4 choose 2. What do I do here? Multiply or add? Multiply, because those are sub-assemblies. At the end, I assemble. They are not alternatives. It's not I choose either 3 or 2. I need both. Agree? So if I need both and I assemble them together, then are you okay with this? So, you see, always break it and ask yourself, imagine yourself building it or putting on the wall 5 cards and say, what do I need to decide? And then what is the flexibility that you have? You count all the flexibility. Don't make any special assumption. These are homogeneous here. So if I choose queens, it's the same as if I choose 7s. So that's why we are under reasoning. But for example, you can ask yourself, what if these are queens and these are 7, just to see how it reads. Then of course you say, why queens and 7? It could be anything you want. So that's it. All right. Let's go to binomial coefficient. That's a very important topic in mathematics. And if you didn't have it before, it's long overdue in your math education. That you don't need to wait to learn calculus and then to learn binomial formula. That comes into basic mathematics, and it's very useful, very important. So what is binomial formula all about? Can you use the title screen? I choose this. So 4.4 binomial. Binomial formula gives you a way to raise binomial to a certain power quickly. And you already know some versions of that formula. What would it be? You know how much is a plus b squared?
A squared b squared.
A squared plus 2ab plus b squared. And then maybe you forgot this one. A plus b cubed.
A cubed, b cubed, 3a squared, b 3ab squared.
Bravo. But I'll write it a little differently. A cubed plus 3a squared b plus 3ab squared plus b cubed. And you will see in a moment that this is the pattern. So, what happens? Actually, my question is, but what if I need a plus b to the fourth? Then, what's new? Formula is attributed to Newton. He noticed the following. Let's look at the pattern here. Forget the numbers. Let's look what happened with powers of A and B. A starts with power 3, which is the same as the power you are raising to, agree? And on each line, what happens? A loses one power and B gets it. Altogether, it's always 3 together. Do you agree? So what would you just predict? No one guarantees, that's not approved. But what would you expect if the pattern continues? What will it be on the next line? Will it be 8 to the 4th, yes or no? Then what?
4.
A, Q, B, I don't know number. Let's disregard that for a moment. Then trade one again. A squared?
B squared is
Then what?
A, B cubed.
And then all 4 go to B. Like A is giving 1 by 1 to B, and finally B gets them all. Okay? What's missing?
Coefficients.
Coefficients. That's what happens. And now I regret that I erased Pascal triangle. Look at the coefficients. 1, 3, 3, 1. That's what Bijan told us. 1, 3, 3, 1. Is that exactly line on 3 on n equals 3 of the Pascal triangle? So who will be on this line then? 1, 4, 6, 4, 1. And it's true. That's Newton's binomial formula. So then what? What would A plus B to the n be? The same way, you go A to the n plus a n minus 1b plus a n minus 2b squared. And on the other side goes a b n minus 1 plus b to the n. Do you agree with this type of prediction? It's not proof, it's not fact, this is like by analogy. Who would be here? Nth line, but who is there? And choose 0, and choose 1, and choose 2, because that's who is in the Pascal triangle. And choose n minus 1, and choose. And that's Newton's binomial formula. What would be a closed version to write it? Is it a summation, yes or no? So whenever you write summation formula, you just recognize what's happening and say it there. So, how would you describe like a generic term in this sum? Does it have both A and B? Yes or no?
Yes.
So A to certain power, B to certain power. So what? And then there is binomial coefficient. On top of binomial coefficient, they all have the same top. What is it? What the bottom? Just look at the bottom of binomial. 0, 1, 2, 3, 4. So what can I say? Count them. So can I say I or R, whatever I have there? Doesn't matter, but I don't have, I just want to use the same letter for no good reason, I. So I goes from what? From 0. What is the last value for that I? And that's your I here. But where else you see that I? Look at this. If I is 1, this power is 1. When I is 2, this power is 2. So can I say that B goes to which power? But A, those two together is N. So if this is I, which is what? What's there is left? What is it? This is Newton's binomial formula. Closed version, although this is the same. We also say that this member is equal, we call this member Tn plus 1. I'm sorry, not Tn plus 1, Ti plus 1. Why do we call it Ti plus 1 and not Ti? Because since it starts from 0, if it's fifth, then I is 4. So always order of the element in the, because if it, so here, how much is I in this case? Is this I equals 1? It was 0, 1, but is this first element or second element? Second. That's why to make it for that, so Ti plus 1, you can label it differently, but this is traditional how people label it. This is I plus first member is equal to this. Because we start with 0, so index I practicing how to react to certain changes. And we'll also get some very nice applications of this and maybe some combinatorial identities. At the end, if time permits, like last 5 minutes, I want to, what? Is this a theorem or this is a guess? Guess, because we did 2, 3, 4, we said looks like it, and we did a kind of guess. So this is not a theorem. If you want a theorem, we need to prove it. How are we going to prove it? Deduction. And what will be essential ingredient in that proof? This is the passage from n to n plus 1. Pascal identity will be the essential thing in the proof. And that proof will be just a little exercise. But I'll leave that for the end because it's just straightforward writing. But let's concentrate on a couple of nice applications and things where we have to be careful with this one. So here's one example. I just erased Pascal and identity already. So what do we want to do? Example 441. We want to raise 3a squared minus 5b squared. Is that binomial, yes or no?
Yes.
Can I use a new binomial formula? Yes, I can, but be careful, binomial formula requires plus here. So the only way to have that plus is to do what with the minus? Absorb it and put it on the second one. Generally, if you want, we do it a little faster, but initially you think of negative 5b squared as your second number. And be careful when you raise to the powers to involve both minus and those numbers. So how do you raise this to the fourth power? I'll take first one, which is 3a squared, and raise it to the fourth power. I need 4 choose 0, but that's 1, and I don't want to spend time here. 4, and then what do we do? Just to make sure that I'm not going to mess up the parentheses, I build those parentheses first, and then I fill in the blanks. So who's here? Who's your a now? Is what? 3a squared. Your second one is negative 5. Plus, then comes 6. How do I know it's 6? It's there on the board. It's Pascal triangle or whatever. The same thing now with 2 squares. And I copy exactly the same guys. What else? I continue here. Now again 4. First one goes to the first power. Second one. And finally, second one gets out. Did everybody get this? And that's it. Now it's just real algebra. But something interesting, what happens? What will happen with that minus from the second one? It will do alternation. When it goes to the odd power, it will stay there. When it goes to the even, it will disappear. So this will be like 81, 8 to the, oops, I'm in the wrong line. 81, 8 to the 8. Plus, what is this? It will be minus altogether because of that operation. And what's this? 3 cubed is 27, 108, 540. 540, 8 to the 6. 9 times 20. 9 times 20 is 180 times 8, 540. Good, good. And then now next one will be plus. What would that be? 5 times square is 25. 150 times 9 is 30. Correct? 150 times 9.
That's right.
1350, that's right. 1350 plus or minus? You are looking at the right line? Yes, I guess. So it will be 15 what? 8 to the 4th. And hopefully now they will get better. combinatorics about those questions. For those questions about specific member, it's a good idea to remember this in the form, this ti plus 1. So here it is. I'm going to keep this over triangle, set the following. So example 442, we are raising 2x squared minus 3 over root x to the 20. And they're asking the following. Find the coefficient of the constant member happening here. Can we do the same thing that we just did a minute ago? Yes or no? Yes, we can, but there will be how many members? 21. And then I will say, where's my constant member and read it? Can we do it simpler? Can we just work with the generic member and realize what is I? So generally the problem is that we don't know I, but we'll just keep it undisclosed until we can make a decision. So how much is I plus first member? We said it's I plus first member, formula says, is what? How much is my n in this case? That doesn't change. When E, choose what? I or I plus 1? No, I. Because as I said, which member is this? Is this third member or second? You know, line up. 1, 2, 3. Is this the third member? Yes or no? How much was I on that member? Was it 2 or 3? 2. Because I choose 2 there. Why? Because you choose 0, 1, 2. So if you choose I to be 2, your member is third. So that's why we have that shift here, Ti plus 1. So Ti plus 1 is 20, choose I, A to the 20 minus I, B. So that's, I just call this formula with a special case, n equals 20, and I undisclosed. Then what do I do? What do you normally do in math? Do you understand the start or something's confusing? You don't look too enthusiastic. Go ahead. What's bothering you? I plus 1. I can, you don't have to call it Ti plus 1 if you want. You can call it Ti, but at the end, when you give the answer, don't forget to raise I by 1. Because if I is 7, that's not 7th member. Which one is it? 8. So that's what this I plus 1 does. Otherwise, as I said, I just call this formula, and then that's I plus 1. Or as I said, you don't have to call it. Say this is the member, and then this member should be constant. Should be constant. So what do I do? I just do the algebra. How much is my A? Who's my A in this case?
2x squared.
So 2x over here goes to 20 minus I. And how much is B? Negative 3 over root x equals 1. But unfortunately, I don't know what is I. So who will tell me who is I? Numbers or x's? Because if I want constant member, that means x must cancel out. X must disappear. So that's why I will particularly pay attention what's happening with x's, and I'll just copy the number. So 20 choose I, doesn't bother. 2 to the 20 minus I doesn't matter. This is what matters. X to the 40 minus 2I. How did I get that? When you raise x squared, 20 minus I, what happens? You multiply the exponents, and that's what I do. Then times negative 3 to the I, and times, what about this? 1 over square root of x to the I. What would that be? A little algebra here, raising 1. What would that be? 1 over square root of x, that's x to which power?
Negative 1.
Negative 1 half. And then raised to I, so how much is that? X to which power? Negative 1 half I. So what happens? Forget which member will be constant? Member that has I equals 16, which is which one? 17. So T17 equals, now I don't need to follow all this. I can just go to the square one and say T17 is 20 choose 16. 2x squared to the fourth, because 20 minus 16 is 4, times negative 3 over square root of x to the 16. And hopefully when I do all this, if I did a good job, hopefully I should get a constant member. Of course, I don't want to calculate 2016. What's better? 20 choose 4. Then times 2 to the 4th times x to the 8th times 3 to the 16 because negative disappears over x to the 8th. Because square root of x to the 8th and x to the 8th cancel, so we did a good job. Here's our answer. So that member is huge. So 17th member in this binomial expression is equal to this. Of course, you can multiply it and get some millions or whatever. Which more than it. Because it's a huge number. Here's the way to do it. So instead of writing all members and choosing the good one, we actually check the design to find out which one will give us what we want, and that's how we solve it. Next, a really beautiful application of binomial formula comes out of famous Moivre's formula. I don't know if you saw it. Sometimes professors mention it in their pre-calculus class, and most often not, because it's not part of the program. So, just a little Moivre formula. What is Moivre formula telling you? Formula says the following. Cosine theta plus I sine theta. What is this? It's a complex number. You don't even need to know that it's a guide. It's just a complex number. And then Moivre found this fascinating fact for that time. When you raise this to the end, it happens what all the three students accept. We don't need to learn triviality, it behaves nicely. So you just multiply and something like this. Cosine n theta plus I sine theta. And how did he get that? That's a different story. By the way, I can give you one very reasonable description why is this true. If you are taking linear algebra, maybe you will discuss that. Because what? Cosine theta plus I sine theta is a complex number. It's like on a unit circle. Cosine theta plus I sine theta generally, that complex number represents rotation by theta. So when you take, for example, number z, and you multiply it by cosine theta plus I sine theta, you know what happens? Your z, wherever it is, gets rotated by angle theta. So here is z, here is 0 theta. So multiplication by cosine theta plus I sine theta is just rotation. And that's interesting because if you look at the matrices that you use most often, 2 by 2, in linear algebra, you either use most often translations or rotations. And then those rotations are actually nicely representable by complex numbers. What is this telling you? Is this rotation, yes or no? That's what we said. We want to see this as rotation. What's the story on the left? I rotate, let's say, by 20 degrees, and I do that 9 times. 20, 20, 20, 20. Is it the same as doing one rotation by 180, yes or no? And that's what it says. Rotating theta, 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 theta 4 times is the same as rotating once by 4. So that really catches this geometry. Nice formula. But here's what I wanted to show you after we accept Moivre's formula. theta, probably nobody knows by heart. 5 theta, it's even more problem. So, what if you need cosine 5 theta? How would you come? You have half an hour to earn $10,000 to have cosine 5 theta. What would you do?
You start by breaking it into 3 and 2.
Exactly, and then, so here it is. Cosine of 3 theta plus 2, which is what? Cosine 3 theta, cosine 2 theta, minus sine 3 theta, sine 2 theta. Is this a good start? Now what? Now you need to break in 3 theta into 2 theta and theta. And then to use 2 theta and distribute, and half an hour will do. Okay? And here is how power of Binomial formula does this in 1 minute. So, you know, like that. And not only that, there's the bonus, we will get sine 5 theta as well. How? Here's the story. I use Binomial formula and I say the following: cosine theta plus I sine theta to the fifth equals cosine 5 theta plus I sine 5 theta. Do you understand where I got this? This is Binomial formula for 5 rotation by theta. Then, on the left one, I will use is this binomial, yes or no? So this will do. Cosine to the fifth theta plus, who's my coefficient here from Pascal triangle? 5 choose 1, which is what? Do I have Pascal somewhere? Well, when 5 choose 1 is fine. This will be cosine to the fourth theta times I sine theta. Plus 5 choose 2, which is 10, or Pascal triangle, cosine cube theta times I sine theta squared. Is this what we learned today? Who's next one? 5 choose 3, which is 10 again. Cosine squared theta times I sine theta cubed. Is there more? I didn't say it's going to be short. I said it's going to be quick. Plus 10 cosine theta I sine theta to the fourth. And who's the last one? Not 10. Sorry, not 10 anymore. Who's here? 5. And the last one is I sine theta. Do you understand this calculation, Monk? Then what do? I just calculate a little more precisely. This is cosine if theta plus 5I cosine 4 theta sine theta. The algebra, I just pulled the I in front. Now comes something important. When I square I square is what? So I pull that negative here, I get minus 10 cosine cube theta sine squared theta. I is gone because I squared is negative. So I first take care of I. I cube is what? Negative I, because I squared times I, which is negative I, so it will be minus 10 cosine squared theta sine cube theta I. Sine to the fourth is 1, so I don't need to worry about that, so I just get plus 5 cosine theta sine to the fourth theta. And then I to the fifth is just I, so it will be plus I sine to the fifth. Did you understand this calculation? And I will compare, and this is all equal to this. And then what? When two complex numbers are equal, a real part and a real part are equal. So here's my real part. Who's my real part? Cosine 5 theta. And here's my $10,000. Don't you agree? Those guys that don't have I, altogether, there's the formula for cosine 5 theta. What else is the bonus? Those guys that do have I, they will give you what? Sine 5 theta. So here is sine 5 theta without I. Was it nice? Of course, power, the main beauty is not in the binomial formula, it's in Binomial formula spectacular. And then we just binomial formula together with Mark's formula. This is one of the homework problems. Yes.
Another application is in physics, in elementary physics. A lot of differential equations that arise from physics have not nice solutions or no closed form solutions. And so what you do is you do a quick binomial expansion to first order, and then it makes it a solvable differential equation.
Okay, so you are using it for approximation. By the way, there's also binomial expansion. Is this binomial formula only working for integers, or is it working also for non-integers? Did I assume that n is integer, 1, 2, 3, 4, 5, the Pascal triangle and everything? The question is, what do you do if they are not integers? There is a way, but then you need Taylor series. And if you open your Calculus 2 books, you will see on Taylor series, there is Taylor series for binomial parts as well, but that's infinite series. It's not this nice, but looks very similar to this. So if you have like a plus x plus 3 to the 1/2, then you can do binomial formula. But an infinite series also uses binomial coefficient. Just open your Calculus 2 books. If you care, when you have Taylor series, then you will see that there is a way also to kind of approach non-integer exponents as well. What else? One very important identity about binomial formula is the following one. I don't know if we'll have time for the proof. For the deduction proof that I promised. And here's the formula. Actually, before I write the formula, let me again copy Pascal triangle. 1, 1, 1, 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1, 1, 5, 10, and 5, 1. Is this my first 5 lines? All right. Let's add up all the coefficients on the same line, like this one. This is line number 4. Those are chooses out of 4 elements. When I add them up, what do I get? 16. All right, let me add these guys. When n equals 3, what do I get? Here. 4. What about here? Predict. Don't even add. What do I get? In line, and sum of the coefficients is 2 to the n. Looks like it. So what I just saw is given n choose 0 plus n choose 1 plus n choose 2 plus n choose n equals 2 to the n. Can you prove this? We can do it by induction, but it wouldn't be pleasant. And if I pay the price to get binomial formula, then I don't want to do induction again. So how would you prove this? Actually, it's very simple. If you look at the binomial formula that says a plus b to the n, n choose 0 to the n, plus n choose 1, a minus 1b, plus n choose 2, a minus 2b squared, plus n choose n. Is this binomial formula that you had a minute ago? I said no. Then what? If I wanted just to get coefficients themselves added up, I should somehow erase a and b.
Make it equal to 1.
Make it equal to 1. So let's make a equals 1 and b equals 1. So what do we get on the left side?
2 to the n.
1 and 1 is 2, so we get 2 to the n equals n choose 0, n choose 1. Was it an easy proof?
Yes.
Now the question. Give me the modeling reason. Forget binomial formula. Why is this true? Modeling wise. What are these chooses from Monday's lecture? I'm having n elements. Here are n elements. 1, 2, 3, 4, 5, 6, 7, 8. I'm just on my drawing 8, n will be 8, but n is arbitrary. It's better sometimes. This is not proof. I always tell you proof is never about example. But I'm just following my illustration with basic. So here it is. How many subsets do I have out of this set of 8 elements? Did we talk about that? a subset of these n, how rich could be that subset? Could it be just with the no elements? Could it be empty subset? Yes or no? Could it have one element? Could it have two elements? Let me skip the other two. In how many ways can you choose a subset with two elements? You have n, you are choosing two, it's a subset, that means the order doesn't matter. Does this ring the bell? You are choosing two out of n, order is not important, because for subsets, order is not important. What's that? Is that a choose? So here it is, all the elements to be classified according to their size. So who is here? All those that have how many elements? Out of n, I chose how many? Two. Who's there? 1, 2, 1, 3, 1, 7, 1, 8, 7, 8, and so on. Then, do some of them have three elements? So on. Is there a subset where everybody's in? Yes or no? In how many ways can you do that? Choose that. Did I forget two of them in the beginning because they were not indicative? Who's there? You cannot choose single ones? In how many ways? And you cannot choose nobody, which is empty set. In how many ways? One way, which is empty. Is that exactly our formula? So generally, model-wise, it tells you here are all the subsets counted without discrimination, and here you classify them according to the size. So subset with no elements, subset with 1, 2, 3, and elements. Each subset must have one of those options, really. So that explains why is this through not using formulas, but using laws of nature. And I think that's what I wanted to tell you here. Just one comment, and then proof by induction. I'd like to show you this proof. You can read it, of course, from the notes, but maybe to see it on the board again when I answer your questions on Monday. We'll talk about the proof of binomial formula, because it's nice exercise in induction. But let's comment in this minute or two the problem that's on the screen. What is that? Summation formula, and then somehow I just arranged